morning, everybody. My name is Bhanu, and I'm working on a project called Development of Earthquake Early Warning System for Northern India. So I'll not make too technical presentation, but I'll just try to explain what earthquake early warning system is and how it is developed in for India. See, the image that you are seeing right now in your screen is perhaps the oldest seismic instrument known to the mankind. This was developed way back almost 2000 years ago in China. And there was a scientist called Zhang. I'm sorry if I'm not pronouncing his name correctly. He was a renowned scientist, astronomer, geologist, and he invented this instrument. What you are seeing is there are four dragons which are hanging through a pot. There are actually 8 dragons, 4 are not visible. And then there are frogs with their mouths open. What used to happen was, if there is an earthquake, one of the dragon will open his mouth and a bronze ball will fall in the mouth of the frog. And as soon as the ball falls, a siren will blow, a small siren. And the 8 different dragons are there because only that dragon will open his mouth. Nobody still knows the mechanism behind this instrument. And many people at that time also are very skeptical whether it will work or not. But anyway, since he was a very renowned scientist, this instrument was installed in the court of king of that time in the city of Lyon. And this instrument was kept there and it didn't work for many years. But then suddenly in 138 AD, one of the dragon opened his mouth, a ball fell on the mouth of frog, and the alarm, alarm was issued. But nobody felt the earthquake. So most of the people said that this instrument is not good, and there was not very good communication at that time. So this instrument was kind of written off, and the scientist Zhang lost a lot of reputation. But few days after that incident, somebody from the and what this instrument said was there is an earthquake is coming from the west direction. But after some time, a person from the west direction, from the city of Longzai, came to the Lyon city, and he told that in his city there was a very big earthquake, and because of that, the whole city has been turned into is in ruins now. When the inquiry was made that when was the earthquake came, what was the time, surprisingly, that was exactly when the dragon has opened his mouth. I was just telling about this instrument, and as I told you that somebody after many days came to the city, and then they said that there was an earthquake exactly at the time when this instrument issued the warning. And this surprisingly, or perhaps was the first earthquake early warning issued to the world, but nobody noticed that. And for almost 2000 years, nothing happened in this field. Then in 1868, a scientist called Cooper in California gave the first concept of the earthquake early warning system for the modern world. He wrote a paper about that. He told how the earthquake early warning can be given to the people. And then again, surprisingly, for 100 more years, nothing happened. But in 1979, as I was telling, earthquake early warning is not earthquake prediction. Prediction would be to inform, tell about the earthquake long before the earthquake comes. What we are doing here is just telling the people about the earthquake after the earthquake started, but not reach them. So, in terms, earthquake early warning is used to describe the real-time earthquake information system that has the potential to provide warning prior to significant ground shaking. Why we need earthquake early warning system? We need earthquake early warning system because most of the civil engineering structure worldwide, and especially in the developing countries, are not earthquake resistant. A large number of population is residing in such structures in the areas which are highly earthquake prone, and the structures are not good. So the only long-term and the perfect solution is to construct the houses which are earthquake resistant or retrofit all the existing houses. But this solution is not economically viable because a lot of money and a lot of time is involved. So in such a scenario, a warning or the earthquake warning could be a very important development in the field of earthquake-related short-term disaster mitigation. Now, what is the working principle of earthquake early warning? The principle, in principle, earthquake early warning system is very simple. We know there are two type of important waves that are created or generated when an earthquake comes. One is the P wave, which travels at a speed of around 5 to 6 kilometers per second. But this wave does not carry any energy. So this wave is not even felt by the human beings, and it does not cause any damage. Whereas the S wave, which travel at a speed of around 2.5 to 3 kilometers per second, carries maximum energy and is felt by the human being, and this is the wave that causes damage. So technically speaking, S wave traveled at a speed almost half the speed of the P wave. And finally, we can use the communication technology which travels at the speed of light to disseminate the warning. Now, this picture shows how it can be done. See, what you are seeing here at 3, where my cursor is right now, is a city. Here is the epicenter. Here where the earthquake has occurred. The red envelope that you are seeing is a envelope of the S wave. The dotted yellow envelope is the envelope of P wave. Now imagine a scenario that earthquake has occurred here. The waves have traveled, and the first seismometer has detected the P wave. There are many seismometers installed. Now this seismometer, as soon as the P wave comes, sends the information to a centrally located processing unit. And if this processing unit finds that the earthquake is large enough to cause damage to the city, it will issue a warning to this city through mobiles, through sirens, through TV, through radio, all the possible means, whichever means are possible. So by the time this S wave, which has reached here, reaches city, the people will have enough time to save their life. We definitely cannot save property. We definitely cannot reduce the damage, but we can definitely save a lot of lives. Now, how to do that? How to find out whether the earthquake is big enough or earthquakes of large magnitude from the initial 3 or 4 seconds of the earthquake? So these are many parameters which have been invented by many scientists. One is called the cumulative absolute velocity CAV. One is called the bracketed cumulative absolute velocity BCAV. Then we have a windowed bracket cumulative average velocity BCAV-W. We have a predominant period parameter, we call it PD. We have a characteristic period, we call tau p. We have an integral velocity square. We have a low pass filter peak displacement PD, and we have a log average period. In India, we are using the low pass filtered peak displacement for the development of earthquake early warning system. We can use many of these parameters, but since PD or the low pass filtered peak displacement is the easiest one, and this is the one which has been most robust for predicting or for estimating the magnitude of the earthquake. In this picture, what you are seeing is the first thing is the acceleration, the second is the velocity, and finally is the displacement. So what you are seeing here is in the red, where my cursor here is, this is the initial 3 seconds of the earthquake. This is the P phase. The S phase is not here. In this 3-second window, we estimate PD. And the research has been done, and it has been found that if in initial 3 seconds, this PD is more than 0.5 centimeter, then the resulting, then the earthquake that has created this wave would be of a magnitude greater than 6, and we can safely issue a warning. Now, earthquake early warning can be given in 2 ways. One is we install the sensor right at a place in our building and attach an alarm system to that. That sensor will detect the P phase, which is not detectable by the human being, not experienced by the human being, and it will blow a siren before the S wave arrives. The basic principle is that P wave travels faster than the damaging S wave, but since only one sensor is installed at the location, the chances of false or missed warning are too high. This is mostly used by the railway, metros, and industries. The other thing is a regional earthquake warning system. This is the one on which we are working. In this system, the sensors are placed in a place in the area where the epicenter is expected or where the earthquakes are expected. The good thing about the earthquake is that, however, we are not able to predict when the earthquake will come, what will be the magnitude, but we can tell where the earthquake will occur. Like in Himalaya, we know that the area between in the central Himalaya, in between Chamoli and Uttarkashi, is the place where the earthquake will originate. When, we don't know. How big, we don't know. So we install the sensors at the places near epicenter. These sensors are sending data continuously to the central server, where this data is processed. And if an earthquake is created there, has occurred there, and our system says that earthquake is of magnitude greater than 6, we issue the warning to the site places which are located far away from the epicenter of the earthquake. So basic principle is pick the earthquake near epicenter and use the present day communication technology to issue the warning. Since in this system we use more than one sensor, the chances of false or missed alarms are very little, and this can be used to save lives. So this is a technical aspect of regional warning system. See, what you're seeing on the top is this is actual data recorded by our system. The first initial portion is the P wave. The bigger one is the S wave. This initial portion, which we call P wave, it does not cause any damage. And this phase is the one which causes damage. You see the S phase. What we do in the regional warning system is we pick at least 4 stations. See the first station, in this 3-second window, it sends the data. The second, the third, the fourth. From these 4 stations, we estimate the possible magnitude. See, why I'm telling estimate is, once the whole data is available to us, we can definitely tell what is the magnitude of the earthquake, but we cannot wait this long. So we are picking this portion only, initial 3 seconds, and estimating what will be the magnitude. And if this magnitude is greater than 5.5 or 6, we issue the warning. This slide has a little bit of animation, and it will explain the regional and the on-site warning system. See, in the on-site warning system, the sensors are installed at the location where warning is to be issued. We have put a threshold line. If the acceleration crosses any of this value, the alarm will be blown. The shaking starts here. An on-site warning is issued here because this is the point where the threshold has been crossed. Now, this animation will tell you what the regional warning system is. See, this is the threshold limit for the on-site. The shaking has started here, and our first sensor has detected the wave, second has, the third sensor, the fourth sensor, and we take some time to estimate the magnitude, and now we issue the warning. And the on-site warning will be issued here, whereas the regional warning has been issued. The on-site warning will be issued here, whereas the regional warning has been issued here. And S wave has arrived at this instance of time for this particular case. So you can see that the lead time available by the regional earthquake warning system is this much, which is almost 70 seconds. Whereas the lead time available by the on-site warning system is this much, which is almost 25 seconds. So you can clearly see that with the regional earthquake warning system, with 4 sensors, a lot of lead time is available. A lot of things can be done in the 70 seconds. Whereas in the regional on-site warning system, only one sensor is used and the lead time is 25 seconds or less. So the time given to the end user is very less in the on-site warning system. I'll tell you a little bit about the existing early warning system worldwide. The UREDS, which is the first earthquake early warning system, which was developed for the railway in Japan. UREDS, then compact UREDS, SASMEX, which is a seismic alert system for Mexico. E-Alarm, which is a earthquake early warning system in California. Then earthquake early warning system in Taiwan. Presto, which is early warning system under development in Italy. UREDS. In 1979, Japan already had fast-moving trains, and Japan has frequent earthquakes. So what they wanted was that in the case of an earthquake, the trains should stop automatically. So an EEW system called UREDS, which is called Urgent Earthquake Detection and Alarm System, was invented by Nakamura. And this actually was the first P-wave detection alarm system in the world. But this system, UREDS, takes around 4 to 5 seconds to estimate the earthquake. But 4 to 5 seconds was too much for railways. So they requested to have a lead time in the range of 1 second after detection of first P wave. So a new UREDS called compact UREDS was developed, and it has a warning times of only 1 second. As after 1 second of the detection of first P wave, it will issue the warning. A SASMAX is called the Seismic Alert System of Mexico. It basically has two components. One is the Seismic Alert System of Mexico City, which is called SAS, and the Seismic Alert System of Oaxaca City, which is called SESO. Now, SAS has around 12 sensing field stations, whereas SASO has 36 field stations. The field station FS means sensor. It started working in 1991, SAS, and for the Seismic Alert System of Mexico, and the Seismic Alert System of Oaxaca City started working in 2003. Till now, SAS has given 13 earthquake early warning as public alert. As public alert means the warning was issued to the public, and 54 preventive alert, where it was not the warning but an alert that an earthquake is about to come. Whereas SASO has already issued 6 public alerts and 5 preventive alerts. California is working very hard to have an earthquake early warning system, and they have created a regional earthquake early warning system. This is again under development. It has not issued any public warning. The working principle remains the same. Detects the P wave near the epicenter, use the amplitude and the frequency content of the P wave to estimate the magnitude, estimate the hypocentral distance of the event, and issue the warning. It is mostly based upon an earthworm like environment, and they have modified it. The US Berkeley has modified it. Taiwan again is a very small continent, and they have a very frequent earthquakes. Everybody knows about the Chichi earthquake. They are also developing an earthquake early warning system for their island. Their earthquake early warning system is based on the earthworm environment. Taiwan is also using PD method to estimate the magnitude of the earthquake, and this system can provide a warning to the areas which are located at 70 kilometers from the epicentral distance. So almost the lead time available in Taiwan is around 15 to 20 seconds, and they're working hard to make it up to 25 seconds. The one thing that Taiwan has done is Taiwan has used a large network of the sensors using very low-cost MEMS sensor. Nobody is using MEMS sensor other than Taiwan and India because they are very low cost, and a large number of network can be created. Presto is a probabilistic and evaluationary early warning system which is under a very in a nascent condition. It's a very early stage of development. It is being developed by Italy, and so far it has not shown very good result, but their research shows that Presto can estimate the earthquake location and size. By size I mean magnitude, within 5 to 6 seconds after the event, after the start of earthquake. I talk about what is being done in India. In India, we started working on earthquake early warning system in 2012. In 2013, Ministry of Earth Science sanctioned a project for development of such system in India. We have already installed 84 sensors which are streaming real-time data. These 26 stations are installed in a network of NIC, SWAN. 58 stations have been installed inside the BSNL BTS towers. They are connected by VPN. We have already developed algorithm for real-time processing of the data, and we have already developed algorithm to issue warning. We have done many simulations using recorded data to test our system, and so far it has shown good result. We have already been able to issue 2 warning in our lab. We are not going to public right now, but in our lab we have already issued 2 warning with a lead time of around 25 seconds in Roorkee. That means if a siren was installed, people in Roorkee would have had 25 seconds to respond. The figure you are seeing right now on your screen, the yellow and the red marker is the current network that we have installed. There are around 84 stations. Where my cursor is, this place is Joshimath, where Badrinath is located, and in extreme left is the Uttarkashi. And many seismologists say that this is the area where a large magnitude earthquake is expected. And many research have been done that if there is a 7+ magnitude earthquake in this area, then Delhi, which you can see in the lower left corner of the image, will receive very, very severe damaging S waves. And as you can see, this distance is almost to 300 kilometers. So technically, through this system, we can give a warning time of 75 seconds to Delhi. This perhaps is the largest time available for an earthquake early warning system anywhere in the world. The yellow marker that you are seeing in the center where my cursor is right now is the place where we are going to install sensors in next year. We have already received a project for this, and we are trying to install these 100 more sensors within this year. Through our system, how the earthquake early warning system will work in case of on-site, this slide will explain. See, the earthquake has come near Badrinath, and as the waves travel, the warning is issued. But you can see, warning is not issued together. As the waves are reaching to the different location, warning is issued. So this is how the on-site warning system will work. This is already in place. And how the regional earthquake early warning system, which is our actual research, how it will work. See, the earthquake has come at the same place. The first sensor has sent data, second has sent data to Roorkee, third has sent data, fourth has sent data. We take some time for estimation, and simultaneously we have issued warning to all the places in the place. So technically, Delhi will have a 70-second of warning, which is a huge time to save life. To our system, our testing has shown that Dehradun will receive a 20-second of warning, Haridwar 22 seconds, Roorkee 31 seconds, Muzaffarnagar 44, Meerut 57, and Delhi 76. So as the distance from the epicenter distance increases, the warning time increases. In the initial beginning of the project, the yellow mark that you are seeing, this was the area identified by many scientists, many eminent seismologists to start the project with. So this is the area where we are instrumented right now. The pink line that you are seeing is the main central thrust, we call MCT, and the blue line that you are seeing is the main boundary thrust, called MBT. And this is the current installation. With current installation, this is the possible source of rupture that you are seeing. This is the instrumented area, central server, which is located at Roorkee. And this is the sensor that we are used. As I told you, we are using a low-cost MEMS sensor. It has a range of ±2G. A frequency response is up to 20 Hz. The algorithm we are using is PD, PGA, and displacement is also available. And through this sensor sends data 24/7 to IIT Roorkee. This is one image of the sensor, how this is installed in the BTS. I'll now explain the working of our earthquake early warning system. I'm sorry. See, what you're seeing arrow is the waves, the data that is coming 24/7 to our wavering. All the data is passed to a memory location in our server. As soon as the data comes, we send it to the archive. All the data is archived in our database. We keep a data for 1 month, and whatever, if there is an event in that data, we retrieve it as we delete the data. See, and this wavering is 24/7 monitored by a program to detect the event. If an event is detected, no, monitor the wavering. Yes, we send the event data, means that portion of the wave, to a memory location called pickering. Then we monitor pickering. We see that there are 4 or more picks. That means that data has come from 4 or more sensors. No, keep monitoring. If yes, then using these 4 records, we estimate MPD. If MPD is greater than 6, no, keep monitoring the pick data. If yes, then issue the warning. The concept is simple. As I told you, what we are doing is estimating the magnitude from the initial 3-second data. So a regression has been done. The first regression model was given by Hasayo in 2000. The second regression model. We tested that for an Indian data set. What you are seeing here is the actual magnitude in the x-axis, the estimated magnitude MPD in the y-axis. So you can see that for a 6 magnitude earthquake, all the events which are less than 6 have been underestimated. And this is actually very good for us because we do not want to issue warning for the event less than 6. So if they are underestimated, it's good. But what you can see is for a 6.8 magnitude earthquake, it is on the line, that is the estimation as well as the actual magnitude is correct. The same is the case with another regression model given by Professor Hu in 2006. Here you can see that all the events are a little bit overestimated, but say a 5 magnitude earthquake is not overestimated as 6. It is still in this box, which means we will not issue a warning in this box. But a 6 magnitude earthquake, 6.8, this is a Sikkim earthquake data, and it has been estimated as 6.8 correctly. This is a slide which shows the error in the Who's regression model and the Hasayo regression model. This is a little bit exercise done by us on the Japanese data set, and you can see that the bigger earthquakes are right on the line, so we don't miss them, whereas the smaller earthquakes are still overestimated, but not as much as to issue the warning. So the model is good for us. The most important application of earthquake early warning system is saving life once the fully developed comprehensive earthquake early warning system is in place. But before that, and in this time, there are many other applications of EW system. One is to monitor the railway tracks, and in case of an earthquake, we can stop the trains. We can have an earthquake early warning system. We can give warning to the important places like nuclear power plant, hospitals, airports, and many other places where the industrial kind of setup where the shutdown of the system can be done by can be mechanized. And one more application of the earthquake early warning system is in the field of active or the smart structures. A lot of research is being done here that if an EW system can tell or anticipate or estimate the incoming PGA or incoming waves, the active dampers behavior can be changed. A lot of people are doing research in this, and this is a very promising field. Now, to tell the gravity of the situation, how much means dangerous or how much devastating earthquake could be in the northern India. This is a little bit of statistics that was given by BMPTC in 2008. It is based on the 2001 census data. What you are seeing here is that in case of an earthquake, in this area only, in western Uttar Pradesh, there are around 98 lakh houses which are at moderate risk. This data shows that every house has a population of around 4 to 5 people. So you can see that around 5 to 6 crore people are in dangers, are living in houses which are susceptible to moderate risk in case of an earthquake, and a lot of these people can be saved in case a successful EW warning is given. What we have done so far, we have developed the dissemination system for the earthquake early warning using internet, using radio. We have also developed a microprocessor-based device for server and for siren. We have made our system, I will not say hack-proof, but we have done almost everything that can be done so that nobody can hack into our system and issue a false warning and create chaos in the city. We have also made provision to check the health of dissemination systems. Recently, we fitted sirens in the campus of IIT Roorkee. We are still not allowed to go to public, but IIT Roorkee, with the permission of director, we have installed sirens. The most important part is to inform people what to do in case of an earthquake warning. Has happened. For that, we have prepared videos which are continuously running in IIT Roorkee's mess. We have created posters, pamphlets. A mobile phone app is already ready, which is distributed to the students of IIT Roorkee. We still cannot share it to the other peoples. ShakeMap software is developed. We have developed a website called EASNI. It's the abbreviation of Earthquake Alert System for Northern India. And most of the things we do are updated here. You can also find the recorded data in this site. This is one of the siren which is installed at IIT Roorkee in the hostels. Another siren. This is the microprocessor box which takes the decision when to issue the siren or not. These are the training modules that we have created because people must know what to do in case of an earthquake. Like the people who are residing the ground floor or the first floor can actually come out in case of a 30+ second warning. But people who are in the classrooms, mess, where there is only one exit, or people who are in the +2 or +3 story, they actually cannot come out. But then they can do a lot of things which can save their life. See, one of the method is drop cover and hold on. The best thing is get under a study table or bed or some corner where the falling object will not fall. This is one of the development that we have done is the PGA peak ground acceleration map of the real time. This was created in real time for an earthquake which occurred on 30th of January 2016. See, what happens is as soon as the waves come and we found that the earthquake is there, we create this map and upload it. This map is not useful for the public, but this map is very useful for the disaster mitigation authorities, because this map will tell where the PGA is high and where the immediate help needs to be sent, because most of the time after earthquake, the communication system will fall, communication system will be shut down. So it will be very difficult to talk with the people. But if you have an estimate where the damage is more, you can actually mobilize your disaster team. Since the installation of our sensor, we have been able to record almost all the earthquakes. And in 2 of this earthquake, we were actually able to issue warning in the lab. We have around 17 in this list. There are 5-6 more. A lot of research work is being done in IIT Roorkee. PhD thesis, there are around 5 PhD theses, around 7-8 MTech dissertations. A lot of research papers are also published. Now on, the next step is to have acceptance and acknowledgement of the disaster management authorities of the country for making strategy for dissemination of warning. We have already started for this, and we'll be disseminating warning to Dehradun and Haldwani, the 2 major cities of Uttarakhand, very soon. One of the major concerns is to have a low-cost sensors in India. Hopefully, develop them in India because that will be cheap. Expanding our network to cover entire Uttarakhand and then to Himachal Pradesh, because if the Kangra earthquake happens again, a lot of study has shown that up to Chandigarh there will be a huge damage. And if we install our sensors in Himachal, almost all of the Punjab could be given an earthquake early warning system. Next is to install sirens in almost every village, every mohalla. We are starting with the schools. As I told, India, especially northern India, and is the place where the advantage of earthquake early warning system could be maximum. The reason is most of the place earthquake will happen in Himalaya, and most of the highly populated cities are around 300 kilometers. So a lot of lead time can be given. EW system is very promising for our country, especially for the northern India. The technology is already prototype and is developed. It has been tested thoroughly, and the time has come to go to the public now. Thank you.